My name is Zhihao Yuan. I'm a software engineer who works for Broadcom. They acquired Semantic a few years ago. But I joined Broadcom after the acquisition, and I'm currently working on the enterprise security. I have some contribution to the C++ standard and sometimes join the standards meeting. But last year, I was co-authoring the functional ref paper. So if you come to this conference every year, you are probably aware of it, because I think the main author, Victor Romeo, he gave a talk on function ref in 2019 at this conference. Because today my talk will touch some parts of about function ref as well. So let's get it started. So before we start to talk about callable functions in all these 4 languages, I want to start the talk with a silly question. So let's say in Python, which allows pretty much everything because it's a dynamic language and very friendly. Let's say in Python, I have an object. It's a capital case zip file object, and it has a method called read. It reads is a function that accepts a name of the member and give you the full string of the member in bytes. Okay, and let's say I have a high-level function that can take a function that you hand it a name, give you back all the bytes. So only one parameter type string, which refers to a name, and one return type bytes. Let's say I have such an object, and the function, high-level function that takes this. How do I pass something related to the object to this function for? This is a very simple question. I guess even you don't know about Python, you know the right answer. But let's check out what we have in the toolbox, because I want you to iterate over these possibilities. Sometimes we approach the right answer too fast and forgot why. So the first thing in our toolbox could be, we can define a local function. It calls a local variable of the RZ object and calls .read instead of it calls .read, so that it satisfies the interface that the high-level function takes. So in that case, it will be a named local function. But in Python, you can also do lambda. So far, this is pretty much same as what C++ can do, right? And then we also have partial application, where you can bind the object along with its unbound method. This is similar to bind from in C++. We use that a lot in code. I mean, my employer. And then we also have the measure method. So you define it, and then your object suddenly becomes callable. In our case, strictly speaking, we can add __ call to our capital case zip file and make it callable. And I can, inside the function body, I can say, if you want to call the object as a function, call read. In that case, I can pass the object to my high-level function. Well, all these options seem silly if you know the right answer. But let's take a look at one of them. to understand why it is silly. In the case of underscore call, so in Python, you can add underscore call by modifying source code. Sometimes, but the prerequisite is that you own the source code, but you don't actually own the file, which is a type in the standard library. Let's say you own the zip file, which is the standard library file, and you can actually add on double underscore call to it. Now, what about zip file.extract? What if I have another higher level function want to take a callback? That callback takes a member name but returns nothing. In that case, if we defined the call operator for zip file, so that call operator has a pre-existing rule. There's no way to distinguish those, right? You can't say I define another double underscore call to do the same job. The call operator is the same as the operator parenthesis in C++. It has lots of restrictions. First, it requires the type where you add an operator on to be class only. The second, same as double underscore call, you need to own the type. And the third, making a call on the objects needs to have unambiguous naming. That is, you can't say, in this piece of code, I feel that read is more appropriate. The other piece of code, I feel extract is more appropriate. You cannot do that. It has to have a very obvious, non-ambiguous meaning. And of course, the right answer is just use a bound method. So when we are approaching to the right answer, because we are told so, what does exactly mean when we write on this piece of code is what this talk wants to discuss. We are going to go through how to solve the same problem in different languages, how historically they work and what do they do now, and then see how C++ can do better. So let's start with Java. Oh, by the way, all the first three languages that I want to talk about, none of them really has operator parentheses. And Java is a very typical one. But when you think about, hey, if nothing is callable in Java, then how does Java support thread? Thread obviously requires a function, right? Customized function to start the whole thread. Here is what Java does since the very beginning. So Java's thread in the standard library, when initializing it, its constructor takes a runnable object. The runnable is an interface. The standard library defines this interface. And then, in order to use a thread in the Java standard library, at least prior to Java 8, you can implement you can write your own class that implements this runnable interface. And you have to override this named method called run to do your work in a thread. And then you create the new object of your type, put that in the standard threads constructor. So one interesting to notice is that for thread to run, your class has to implement an interface that is specific to thread, right? If your class needs some work that has to be done in another thread-like interface, let's say not runnable, let's say it's writable, what do? Your class needs to implement that interface as well ahead of time. In other words, prior to Java 8, there's no single thing you can do to make an object simultaneously callable to two different interfaces that demand the same signature. You have to prepare all ahead of time. That thing is changed after Java 8 introduced lambda expression. The lambda expression in Java is not only an expression, but it's a full framework to handle this sort of thing. I'll explain this in detail. So for now, on the screen, you can see, yeah, this is so what used to be in the place of the thread constructor was an object that implements runnable, but now I replaced with lambda expression. Lambda expression in Java has no type. Then how this code is being translated. The first thing we should notice that for those interfaces which defines a single abstract method, since Java 8, we now give them a name. We call the same interface single abstract method. Those kind of interfaces are also called functional interface and can be decorated using the @functional interface annotation. The important thing to remember is that it's recognized as a functional interface because it specified a single abstract method, not because it's name of the member function that it's going to call. So this wrong name here, it can be anything. If you have an interface defined a single abstract method called apply, that will be recognized as a functional interface as well. And then at the time you write down a lambda expression, to help our understanding, we can imagine that it is doing a very simple thing. That is, we can create a hidden type. Right? The compiler could choose to generate a type that automatically implements the interface demanded for demanded by the parameter. The parameter type is runnable, so the lambda can choose to implement runnable and fill the lambda's and fill that single abstract method's implementation body with your lambda body. So the implementation I'm showing here is naive because GTK doesn't really do it. But it has a nice property, which is now the idea can be expanded in Java language itself. You reduce the Java type system and can be type checked. So what's the advantage of this model? By saying model, I mean a lambda can be used in place of a SAM interface, no matter what's the name it's specified for that single method. So the first advantage, there will be no magical method. There's no double_underscore call, operator parenthesis, etc. Right? Different interface can choose to pick up a different name for their call operator. And having that, so because lambda adapts to such a named method, so when you write at the user side, which provides this code, can ignore this name. But this name cannot be ignored at call size. That is, by saying call size, I mean the higher level function which takes an object of runnable, for example. When calling it, it still needs to say object.run, parenthesis. That run name cannot be ignored. This is actually an advantage from my point of view, because it makes things very explicit. Sometimes when we take callbacks, we didn't name because there's no other name attached to the callback, which is just parameter name, and sometimes we just name the parameter f, and nobody knows what it does. And not only that, you, as a user side, as a place where you can now write a lambda, user can still opt out to a full class definition. For example, when their code body is too complex, they can still go the old way to write a class that implements this interface. Again, this makes the purpose of your class very explicit, because you have to explicitly say your class implements runnable. Well, if you are familiar with Java enough, you will know that the third item also implies that the whole model is backward compatible in Java. But we can ignore that part, because such an advantage will be Java specific. And let's go back to our original question raised earlier in this talk. Now, what if the method name mismatch? Since Java 8 introduced this lambda expression framework, we can solve our previous problem nicely. The problem can be understood with our higher level function called take. It takes a single abstract method interface, but in that interface, its name is specified differently. In that interface, the function caller wants to call is apply, but as my class zip file offers only read, so the method name mismatches. What to do in this case? Well, very similar to what we did in case of Python. You just say object double colon and your method name. So one way to understand this, well, this thing is of course also called bound method in Java. But there's another way to understand this. That is, I could pass an object zipped, and I did pass the object zipped. But in addition to zip object itself, as this place, I tell the compiler by saying, hey, I'm using an object to fulfill your functional interface. But instead of calling apply on the object, I want you to call read, right? This is a different way to understand this. But how it's implemented, well, we'll get deeper and deeper later. The simplest way to understand this is just bound methods could be a closure. We do the same thing as what we did for lambda. We just create some type that implements this interface on the fly, capture whatever needed to implement it's that single abstract method, and put that new object in place of your bound method. It could work. I'm not saying that it's implemented this way. It doesn't, but it doesn't hurt to think this way. One other thing I want to bring to your attention is that So look at these symbols, these hidden symbols, lambda $1, lambda $2, and my very first object that implements the roundable interface. What are they? What do they have in common? They are all different types, but they are all usable in a function that demands a single callable type. In other words, although they have different types, but they can be used in place of each other, right? Your high-level function asks for only one type that is roundable, but you have the option to supply different types to it. What this phenomenon is being called is type erasing, right? So at this high-level function, let's call it take. Your input is many different types, but after this function inside the function body, you only access one type. That's the type erasure. Actually, all interfaces erase the types. Even though the compiler isn't actually generating these types, we'll get to how GTK actually implements it later. But the outcome will be equivalent to I went through a type erasure. Another observation can lead us to some optimization. So if you look at a single abstract method, it means what? It means in the V table, there's only one single abstract method, right? So instead of having a V table where you have a V putter points to that single entry V table, we could implement this differently. So what GTK actually do is that first, we emit a static method to contain the code. And then we store and call a pointer to that function directly. So imagine that you get rid of a V putter, but replaced it with the function pointer that will be stored in that V table. So if you are a C++ user, you will feel that this step get rid of one level of redirection. But in Java's case, it made JVM it gave JVM more opportunity to optimize this. The level of redirection can no longer be modeled in this case because there's no Java language involved after we apply this optimization. So how to actually illustrate that implementation strategy? So in this case, where you have a class containing our previous examples code, Java has no free function. You always need a class. In this case, where lambda is used, we emit a static method to contain the lambda's code. And then in the class, in this example 4, we attach that static method to the class who owns the lexical scope where the lambda is being written. After that, we generate some call side object to invoke this static method. So as you saw previously, this approach looks very much like moving the function pointer around. But Java has many different kinds of function code to run. So this requires a generalization. They generalize the idea of function pointers. So instead of having an 8-byte function pointer, they say this thing, this reference that serves the purpose of function pointer is called method handle. Behind this, so method handle is typed, strongly typed, but it is dynamically typed. What does it mean is that previously when we saw those hidden types implements your single abstract method, they are of different types, and that type can be reasoned in Java language. Their type implies signature. But for method handle, method handle is not a parameterized generic type, no. It has a member to record its type information. So it has runtime type. And then the object to carry a method handles, which allows you to call, is called call site. Again, this is a single type of runtime type. And JDK will generate that for you. So you may have heard of invoke dynamic, which a call site uses to invoke method handle. The term dynamic here doesn't mean like the code is generated at runtime, not necessarily. It means that we now switch to dynamic typing, because the type cannot be expanded in Java itself. If you ask a Rust guy, they will say, oh, that's an unsafe, right? Something cannot be reasoned within the language. And of course, again, method handle is inside its object layout. It can have different layouts to implement static method, bound method, unbound method, lambda, many different kinds. So that wraps up the information for Java. Let's take a look at a language that is very similar, C#. So C# is famous of its delegates. Prior to C#, I guess there's no languages use this term to describe a function prototype. So the interesting part of C# is that, inside the language, there are lots of objects that are callable, which is different from Java. Java has nothing callable, right? There's only a function, and the function is not even an object. C# has a number of objects can be callable, but classes are not callable. So to pass something callable through a higher level order function, you need delegate. And delegates is actually quite similar to Java's functional interface. Well, in this particular case, delegates for threads is named differently in the C# standard library. It's actually called thread start. But that's only a detail. To compare these two, if you still remember, in Java's case, when the high order function call calls an object of type runnable, you need to mention the method name run as the call site. In comparison, delegate doesn't specify a name for the abstract method. You refer to a delegate by no name, just a pair of parentheses. In Java, we use that simple abstract method to carry the signature of what we want. In this case, it's a method that takes no parameter but returns nothing. Here, in C#, a delegate itself is a signature. And you see it has the same signature here, which takes no arguments and return void. If you replace that delegate keyword to type diff, you'll find that the code immediately compiles in C, and that's the idea. Delegates is a formal function prototype. And how to use it? In the Java's case, you have to have something that implements this interface, right? And implement that single abstract method, override it by matching its name and signature. In C#, delegate is also a type. So interface roundable is a type. Delegate is also a type, but it has diverged from interface. Unlike a type which you can implement, you don't have to implement anything. You can write your own class that implements nothing, inherits from no interface. You can name the function you want to call arbitrarily. In this case, I still call it wrong but it can be anything. And then at the time you pass this object to where to pass an object of my roundable to where it needs to fulfill the need of a delegate, you say object dot method name. Use this syntax to tell the language that this method wrong is my object's unnamed method that do the work for your thread start type. So although this syntax is very intuitive, it wasn't there before .NET 2.0. So before .NET 2.0, you actually need to go ahead and create an object of that type out of a bound method syntax. So if you see this code, you may start to think, wait, isn't this look like our naive implementation of lambda in Java? And yes, delegate can be understood in the same way. You can imagine that for a delegate type thread start, that could correspond to an abstract base class hidden, but has a virtual function that serves the purpose of a call operator. The invoke carries a signature, same as what you specified in delegates. And then compiler can generate a class body which carries all the necessary variables and implements that virtual function. .NET doesn't really do that, but it doesn't harm to understand it that way. What .NET actually do is actually quite similar. Indeed, one delegate type corresponds to an abstract base class. However, when implementing this object of that abstract base class, we use this system provided type delegate. You see that type is not carrying more class members. All those class members, all those data are already in the base class system delegate. And system delegate has slightly more members than what I showed on screen, but the most important two members are target and method putter, where in our previous case, target simply points to my roundable object, and method putter points to a member function called raw. And this time, this function pointer, this function pointer is really a 8-byte pointer. So that thing is not generalized in the case of a delegate. But it doesn't mean that delegates is not generalized itself actually is generalized. So unlike Java, which generalized the idea of function pointer, but hide it from the user at language level. I mean, you can, the method handle type is available in the library, but it's dynamic typed. If user uses it, the experience will be different from having a static typed function pointer. But in C#'s case, the place they place the generalization is delegate itself. The C# generalized the idea of function prototype and exposed it to the user. The delegate is a fat pointer. It at least it needs to carry those 2 pointers. And this graph shows the simplest case, right? When you have the expression that's specified on bound method, if you pass that bound method to a function that the specified delegate as its parameter type, it's going to create an object of delegate behind things. Let the target points to your object, and let the method pointer points to the code where you actually implements that member function. So this model is very simple and has some nice properties. First of all, meaningful names on the call sides are required. This is different from Java. In Java's case, if you implement the interface, you can then ignore that name when passing this object around. And of course, if you use lambda expression, there's no name. The only time when you can specify a name is use a bound method. That is optional. But in C#'s case, this is required. And the model itself is simple. It's a single mechanism that involves no inheritance. So one less things to learn. So before we move on, let's briefly get back to delegates implementation. So previously we mentioned the simplest case, right? You initialize delegates out of a bound method. So both these 2 members are filled with something. And there's another case where you can use a delegate to point to a static method. In that case, we'll generate a thunk. The thunk's only rule is to shuffle the arguments passed in. So you can imagine that this is very similar to C++, right? In C++ case, the underlying function that implements a member function, its first parameter is this. Static member function, its first parameter is just its first parameter. So when delegates being called, there's only one calling convention. It needs to call the method footer by placing target in the first parameter in the static member function. If delegates is binded to a static method, there's no such, the first parameter will mismatch. So what we do is to generate a thunk that ignores the first parameter. The first argument is set as none. So if you get this, and if you are familiar with the function ref proposal, you'll recognize that they are very, very similar. In the function ref's case, we always generate a thunk. We do that for a reason, and there is actually no cost to do that. Anyway, you get the idea of fat pointer. Then it's time to look at it in Rust. Rust has traits. What I showed on screen is not a trait in the standard library. Rust almost has operator parenthesis, but doesn't really need it. I'll explain later why. So on this slide, I hope you can remember how the trait looks like. To simplify things, here I'm specifying a callable type that returns void, and it takes it takes arguments of different types. So Rust doesn't support variadic templates or anything like that yet. So if you want to pass unknown number of types that may be of different type, you have to use a tuple. And then go back to our question. Our question, if we state that in Rust, it will look like this. I have a class in Rust, it's called struct. It has some fields, but within that class body, you cannot specify a member function. You'll have to open a new block to place your member function. And in that block, we have a member function called notify. Then the question comes in a higher order function, which takes an object or a reference to that object or that models the callable trait. I can then call it by calling its named member function specified in that trait. But what would you do to pass this, an object of my type, that is my reporting callback, into the higher order function? So the problem is similar to what we had in Java, right? You have a trait, serves the purpose of a functional interface, specify the name method, and I have called that name method. But you already know that Rust has no virtual, no inheritance. So how do I make cb.call notify instead? And that is where import block comes into play. You can implement the trait after the class definition finishes without consulting inheritance. So a first look at this is very intuitive, a very powerful feature. But it becomes interesting if you start to compare this against other features that we have seen. So there are two ways to look at this feature. The first aspect is that we have a trait in Rust, and it's very similar to a concept in C++, right? I intentionally made these two very similar. In C++, the standard library is still invoke. In this, doesn't specify the return type. And they even have the similar syntax when you use that in a higher order function. You provide the type parameter and say, hey, that type parameter models a concept, right? But now the interesting thing comes. That is because Rust has this import trait for a type. After the type definition is finished, you can retrospectively make a type to model a trait. So the trait in Rust is a part of the type system. Unlike concept in C++. Concept in C++ is only a predicate. It answers true or false. How do you model something that said, how do you say, well, this type used to not be callable? now after you do something, it starts to be callable. Strictly speaking, we have a workarounds to do that. We can define some C++ trait and define our concept in terms of the trait, but there's still workarounds. There's no official, or there's no single way to model a type, to let's say type model an existing concept in C++. So in this specific case, what we actually done is a concept adaptation. The class itself already modeled some idea. That is its member functions, right? It supports notify. It means to be used as object.notify. But our interface is specified differently. So we have a adaptation. In C++ case, although we cannot do it using C++ 20 concept, we could do that using C++ 0x concept, where concept adaptation is explicitly supported. Although, of course, 10 years ago, the syntax is not that nice. The syntax I borrowed Richard Smith's generalized alias syntax. But I hope you get the idea. The concept map in C++ 0x is an input block in Rust. And that is why I say Rust doesn't have to have operator parentheses, although strictly speaking, it has operator parentheses, because once your type implements some special interfaces, you can then call the type outside the generic code. So you can say my type parentheses, but it doesn't have to be the case. And at least C++ 0x concept didn't do it. If you want to use an interface, want to use some functionality specified in a concept, you have to be in a generic context. And what showed on the screen is how actual Rust code looks like in the standard library, where you have traits. You have 3 traits: fn once, fn, and fn mute. Fn mute, it says this function can be called multiple times, but may change its own state. Fn it may be called multiple times, but it cannot change its own state. In threads case, it only needs fn once. And there is another aspect to look at this trait feature. That is, when you write down a generic function like this in Rust, it has a similar restriction as C++, that is the same as C++ template. That is, you cannot expose its declaration and then hide its definition. If you write a generic in Rust, you have to provide its implementation. But there's some option in Rust which lets you to use the trait type as if it is a concrete type. All you need to do is to place a keyword die in front of it. The hypothetical concrete type is called a trait object type. Long story short, this keyword opt-in type erasure. So thanks to the fact that the trait in Rust is fully type checked, its type information is so rich that allows you to build a V table behind the scenes and allows a trait object type to serve the purpose of a interface. So in the second line, when you can actually do that, and when that actually compiles, you can put that declaration in some file and hide its implementation. So after we learned this knowledge, and we take the aspect that the trait is some kind of an interface, then the question becomes interesting. So we know for fact that import can extend completed classes. Okay. And then input block can be split into different modules. So you don't have to provide all input blocks at the same time. In other words, if we use the die keyword everywhere, it appears that the trait object can use more than one V table. What does that mean? So if think about, compare this with C++ abstract base class. When you want to implement multiple pure virtual bases or interfaces in C++, all of this must present before the type, when you declare the type, right? When you provide a class body of that class, you have to list all the interfaces you're going to implement. After your class body closed, you cannot add more interfaces. And of course, that class, the interface, like you cannot say, hey, in this file, I implement the interface A, in another file, implement interface B. You cannot do that. But in contrast, in Rust's case, if you have a interface A that are already implemented, so your class implement already interface A in this file, but then later in a new file, you say, I saw a new interface and I didn't implement it. Then you put an implementation right in the file. That is okay in Rust. So how does Rust do that? It's actually easier to understand Rust trait by expanding them in C++. So let's recall the classic object-oriented programming object model in C++. This is the easy part, right? You have you specify a pure virtual base class, and then have a type to implement it. For that implementation, we generate a V table. The compiler generates a V table for you. The V table is an array of function pointers, statically initialized. And then the object that implements a class that uses virtual functions are different. The layout of an object like that has a so-called polymorphic object layout. Different from non-polymorphic object layout, it has a V-putter in front of it. So the object layout itself is larger. If you want to customize this layout, C++ language doesn't allow you to do so. But C++ is a very powerful language. You can choose to do it by yourself. So very often, when we want some different layout, when implementing type erasure, we handcraft a V table for the type erasure. Different layouts. Think about maybe why don't you, for example, why don't you put the V at the very end? Although I know people are not motivated by that idea, but it's just one example. We'll later see different layouts. So after you have specified the type for V table this way, you can fill that V table at compile time, statically initialize it, right? This will be the same as what a compiler would do to a V table. After done that, we then can have different layout for our type erasure. So as an example, if your type erasure supports value semantics, you can store the object sys in your object storage. Note that here I changed my V. I give my V pointer a type. So I chose reference wrapper because V pointer always makes me feel that can this be none? It better not be. Reference wrapper is more appropriate here because it has a reference semantics and cannot be none. And it also supports moving. So if you assign a different object on top of your existing object, when I say assign object, I mean the whole type erasure. The reference wrapper, what the reference wrapper binds to can be reseated. So it changes the polymorphic behavior after assignment. So the parts on the very left is what a polymorphic, what a type erasure with value semantics would do. And the one down there has reference semantics. So because you can customize the object layout, you can use the same V table, same V footer, but store different things. In the later case, it's not only has reference semantics, it's also non-only. Some types actually use that. We have a paper called proxy. So in its first revision, its object layout looks exactly like that. So one thing to notice is that the example down there uses 2 pointers, right? Actually, we can do lots of things based on 2 pointers. We could say it's not a raw pointer, but it's a smart pointer. In that case, if you are familiar with some standard library types, you'll find that the type erasure that used a customized, a handcrafted V table and some smart pointer that has move-only semantics, that's exactly move-only function, right? Although move-only function has some small object optimization, but you get the idea. So if function is that, you see, I have two different type erasures, but they are of the same size. Both are 2 pointers. So another thing to notice that in this slide, I get rid of the reference wrapper. Start at this point, let's assume that a reference can be reseated as well by a mem move. Exactly what's, by receiving object using memmove is Rust's capability. Assume that this is the case. And then we can say drawable, the customized variable type we previously provide is a Rust trait. Why? Because the type down there that has reference semantics but non-only is ref followed by a trait object type. And the type up there, which has move only semantics, that's a boxed type trait object type. Box is move only a smart pointer in Rust. If we compare these two, we'll find that both of them reference the trait object type. So what exactly is the trait object of that type? A trait object is the shared data between these two things. The shared data is a vputter that points to a trait, and then and followed by a pointer, a raw pointer points to the object. A trait object is a fat pointer. It doesn't know about lifetime or on-tree shape, all of this in Rust, and is opaque in the Rust language. So, but its representation can be examined in unsafe Rust, so that you can build your own types that store trait object differently. But so far, I've seen very few people does that. So we know that the customized vputter we provide is a trait in Rust. And then what is an input block? Well, of course, the variable we wrote named drawable input, right? There's a reason I named that object this way, right? It's just that we don't have such language construct in C++. You can see that this whole thing is very similar to input block. So how to build something similar to Rust traits? Here's a checklist. First, you need a type to carry signatures. And then your vputter needs to be detached from object representation. You cannot mandate that the vputter must appear as a part of the object layout. Last, the input code is ignorant to the object storage. These three gives you the advantage that you can retrospectively model a concept for a type and can freely attach any interface to an existing object. So we changed the idea of vtable and the object layout a little bit. We now give the generalized name. The types that carries signatures, we call them witness table. And the new adaptable object layout, we call that existential container. It seems that at this point we have moved very far from the topic of this talk. It's time to do something real. So how to adapt anything to Callable in C++? What existential container can witness Callable in C++? And what input blocks in that case would look like? So we already know that the existential container for callable in Rust could be, there are many options. In the case where you can repeatedly call the callable and allows the state of the callable object to change, you have three options, right? You can say it's non-owning and has reference semantics. That is ref die mute. It's owning but move only. Box mute. Box die mute. It's not move only. It can be copied. Okay, add die clone in front of it. And they all have correspondence in C++. Well, in C++ 26. In C++ 26, we are going to have function ref and then copyable function. In C++ 23, we already had move only function. After introducing those two types, we can fulfill what is offered in Rust. Now you might say, wait, why this has to be mutable? There's also options for Rust to say that callable doesn't mutate its internal state. It's thread safe. Sure, fine. It's all supported. Okay, we're not sacrificing safety here. So this sums up the choice of existential containers. Now we get back to the problem. In C++, I can encounter the same problem. I want to pass an object my callbacks that has no operator parenthesis to the higher order function accept. The accept is asking for a callback that has the same signature, the same as what I offer using a named member function. But I want to pass my object to that accept function, but instead of calling call operator, I want my function ref call operator. It calls my notify member function instead. How to do that? So in C++ 26, you can do that using a special constructor of function ref. That constructor can be chose using the braced initialization syntax when fill the argument for this function ref parameter. So you can say it's braced something, comma another thing. Those two items are initializing one parameter. Then the student type is a tag type to carry the information about how to generating the thunk that function ref uses. And we can say instead of, we can tell the standard library that instead of calling just parenthesis, you invoke my pointer to member function instead on your target. Like delegates, this mechanism supports static methods as well. In that case, just don't pass the object. If you simply pass to non-type pointer to static member function, it works that way. Well, since it supports static member function, you might ask, does it support explicit objects member function? The new type of member function we introduced in C++ 23. And the answer is yes, of course. Not only that, you can even do this. Provide a full function body at the time of initializing function ref. Note that the first parameter is your target type will be passed into it. So there's no void pointer to void involved, because this is only what you passed in here is not the thunk, it's the instruction that tells us how to generate the thunk. So we made the interface type safe. If you look look at the previous two examples, you can now compare that to our previous arts. Like those previous examples seem to show that this is a pretty powerful feature, but we already introduced every bit that what our previous arts can do. They are just doing the same thing. For example, if you want to specify something differently to call in place of your operator parenthesis, C++ 0x concept can already do that. This is the same as performing a concept adaptation using alias, except in this case, we got rid of all the syntactic noises, removed those from code, and packaged the whole package become very flexible, because you can do this adaptation very close to the time of use rather than have it in one place of the file. And then when you look at the example which allows you to provide a full function body, trait can already do that. The only difference is that in general case, you provide multiple function body for a trait, but here we only have one function body to handle. And by using metaprogramming in C++, we can make the interface type safe here, so you don't need to deal with casting by yourself. In other words, the function body you saw passed as a non-type parameter to stood non-type is a one-time input block. That input block links the use of links the function body using the use of the object rather than relying on the type. The input block in Rust links these two using type. It makes a type model C interface, but for here, we have the object already. We link its use against the interface. And that interface is already specified as a signature you pass to function ref. If you don't like the linking this way, you can always opt out to give it some name. Make this link by name. So you can imagine that you have an option to name your input block rather than relying on type matching. So to summarize the talk, when we think of functional programming, we have been thinking in terms of functions. Right? We got first class functions, sometimes with a call operator. But in this talk, we see adaptation enables function code without parentheses. Why? It's because we may have a misunderstanding in a concept called closure. When we learn closure in in computer science, closure is context plus code. The closure context concept is not about syntax. We never say closure is context plus a call operator. it's something callable, but it doesn't have to be call operator. And unsurprisingly, C++ can often deliver a flexible feature using the same idea, which found in other languages.